Okay, so 4.6b, the oopsies, the cathode ray. So I've got a new piece of equipment here. I'm going to try and get it to work. So bear with me. So the cathode ray is kind of like a light bulb with really, really special features. Okay, now of course it has the name cathode, and that's because this part is the cathode. And of course, cathode is the part of a Z circuit that is negative, so let's just pretend that this was hooked up to some sort of electrical source. And here's your negative, and there's your positive. So, hold up, let me just grab this. So inside your your negative part of the battery is where all your electrons are. Using these terms very loosely, so don't try to correct me later, I don't really care. So all my itty bitty electrons are shooting up through this piece here that we're going to call the filament. So let's just change our color real quick. Boink. And we're going to call this our filament. And just like any other filament that you know, that filament, oops, too many T's, filament, that filament gets hot. Okay, just use the mouse, stop being stupid. Filament. So that filament gets hot, and as it gets hot, it throws off these electrons. They just get flung off. Think of like a ride at an amusement park, but you didn't put your seatbelt on. Okay, so our electrons are getting flung off, and the term for them being flung off is called thermoionic emission. Thermoionic emission. I have no idea if that's spelt right. It sounds dirty. Okay, now of course this positive little loop here, this has a bunch of positive charge on it, is going to attract these electrons through. So yes, some of these electrons are going to hit the positive charges, but some of them are going to be like, yeah, I love positives, and they're going to try and touch, but they don't. They just shoot through. So they're going nice and straight now. So you have a bunch of electrons flinging straight in sort of like a beam. And then that beam hits this part of the bulb, and that bulb is coated in fluorescent type paint, fluorescent coating as they would call it. And when those electrons hit, they will give off a bunch of light. Okay, these plates here are called deflection plates. They can be positive or negative. They're going to make your electrons act a different way. So there are a few parts of the cathode ray that you need to be able to identify. The cathode, of course, the filament. This part is called, some people call it it kind of accelerates the particles as well, or it aims them, but it's just the anode. We'll just call it the anode for now. Oh, that's a great color to write in. So the anode is opposite of the cathode, and then you have this electron stream or beams. There is a difference between stream or beams. 1 second. I couldn't find it. Can't remember where I read it, but it was kind of like a quick note that the examiner made about the difference between streams and beams. Alright, and then you have your deflection plates. This should be a better color. Deflection plate. Alright. Now, the deflection plates normally have a charge, and let's talk about what that charge would do. Let's say that this deflection plate had a positive charge, and this one had a negative charge. What do you think would happen to my electron beam? Opposites attract, so in this situation, my electron beam would curve upwards, and it kind of looks like a ball rolling off a table, but backwards. So if I turned my screen upside down, or I could just swap these around to just explain a little bit better. Make my top negative and my bottom positive. So let's say these were negative and this was positive. It would create a beam then it just looks like a ball rolling off a table. Okay, so that's my electric field. All right, negative and positive. Let's clear the board and talk about the situation when it involves a magnetic field. So let's say this is north and this is south, which means my magnetic field lines go from north to south, right? And I turn on my cathode ray and I get a stream of electrons. Now, if I have a stream of electrons, then I have a current. And this now has to follow, it's perpendicular, so it has to follow that Fleming's rule or Fleming's law when they're perpendicular. So we have down, we have across, so my beam is, now I have to actually do the thing with my fingers. Second finger is current, first finger is field. My beam is going to go into the screen, okay, due to Fleming's law. And I feel like that's the easy part of the cathode ray stuff. Let's get to the hard part. Let me just clear my screen. Alright, so this is a little harder to explain. So we have our filament, and the cathode ray, of course, is shooting off an electron beam. So now we have two sets of deflector plates. One set above and below, and one set to the right and to the left of the beam. So now if I increase the voltage on this, so increase the potential difference, it's really going to make my beam suddenly go up and down, which makes perfect sense. So now my beam, when I increase the voltage, I turn it up, my beam goes up. If I turn it down, my beam will go back down. Okay? And the same thing with my X and Y plate. If I increase the voltage, if I turn up the juice, it's going to go a little bit toward the left or toward the right. So if this was on a screen and I turned my Y up and down, you would see the beam, the circle. So let's just get a big circle on the screen. If I was looking at a screen, you would see, oops, the circle just move up and down. So if I messed with my Y, it will go up and down. Low voltage, high voltage for the Y. If I mess with the X, it'll make it go left or right. Low voltage, high voltage. Makes perfect sense. Okay? So if we were to start twisting with the X and the Y at the same time, and or leave one of them on, it will end up looking up and down and to one side. We call the X gain a sweep voltage. That's what's making it move sideways. So it's sweeping it along. And then the Y is making it go up and down. Okay? It's a little basic, but should get you through.